Hi everybody, welcome to the very first episode of Netzero Academic Life. Today I'm going to talk about Power2X, what it means, and whether that's the viable or maybe crazy idea. So let's get started. Because it's the very first live event in this series, I just wanted to give you a little bit of overview of what I'm going to do. So, the first thing is I'm going to, talk about who am I, what I do, and what kind of stuff you can expect from Netzero Academic. And you already subscribed to the newsletter, some of you did. So you can see I've started posting regularly about different technologies, and I really enjoy the engagement that we have on those newsletters. If you haven't subscribed, please do so. Link will be below. Those lives will be alternating with the newsletter so that we can have additional way to discuss any questions that you can have about the content of the newsletter or about anything about net zero, right? So if you have any questions you want me to answer during those live sessions, please do get in touch. You can DM me on LinkedIn or send me an email, and I'll be discussing those. Another thing is, I'll later, once I show you who am I, what I do, I'll talk about the key idea of Power2X, P2X, whatever you call it, and I'm going to talk about the viability of that. I will show you a little bit of an example there today. And finally, I will briefly talk about how we can collaborate together, how we can, work together in terms of collaboration, teaching collaboration, training collaboration, and research as well. And we'll do the Q&A at the end. Okay, so without further ado, I know everything is working well today, so the technology is on our side, so that's really great. If you have any questions, leave them below in the comment section. Okay, I can see the comment section, or I will be able to see it fairly soon once it pops up. If you have any comments, just leave them in the comment section below. Right. So without further ado, let me switch to my presentation mode, and you should be. Yep. Just very quickly. Yeah, you should be able to see my presentation right now. There's a little bit of tech issues anyway, but right. So let's start with the Tech Zero. So I've started with the agenda. I already told you what we're going to talk about today. So we've got the intro, and I'm going to talk about who am I and what the heck I'm talking about. I'm going to thank you, some of people who already contributed to my work, which is amazing. I'm going to talk about the viability of Power2X in the context of net zero, but also I'll talk about the collaboration. So first of all, thank you all for the support that you're providing on LinkedIn, beyond LinkedIn, on Coffee. I've recently got 14K followers on LinkedIn, which is amazing for me. It just shows the interest, and it just gives me additional energy to drive this conversation forward. Also, thank you for my coffee supporters, people who bought me coffee. Hopefully we get to meet each other very soon, face to face, so that we can get that coffee, and it's on me on that time. Okay, so when we meet one to one, I will get you coffee as well. Thank you for that. So Net Zero Academic newsletter, it got more than 5,000 supporters since its inception in November, I believe, or December. So that's really encouraging again. So big thank you for all of you who support me. I really appreciate that, and thank you for the energy that you give me to do this kind of thing. If you're interested about the net zero and you want to learn more about my newsletter, just go to my LinkedIn profile. It's in the featured section, so you can subscribe if you haven't done so yet. So who am I? About me. That I'm David. You follow me on LinkedIn probably. I'm David Hanak, and I'm a net zero academic. But what this means? Well, in my work, I innovate and assess feasibility of net zero processes, which means I look at how you can design new processes, industrial processes, in a kind of way that doesn't contribute towards global warming, which means that the net emissions of that technology is zero or carbon or negative. So this is what I do in my day job, right? So as an academic, I do innovate and create those technologies test their techno-economic feasibility, test their life cycle emissions, and just want to ensure that there is a business case for that, and the environmental side is also viable. Okay, so I've been doing that for more than 10 years now, almost, with the main focus on carbon capture, direct capture, CO2 utilization, hydrogen production. So if you want to talk about any of those areas, this is where my expertise lies, but also I've been doing some work on wider energy technologies, heat pumps, power generation cycles, SBTIs, and all of this stuff. So if you've got any question about energy, I'm happy to help. Okay, so this is very quickly about me, and let's move to the main topic of this live session, which is the Power-to-Gas, Power-to-X in principle for CO2 use. Okay, so the question that I keep asking myself, and people ask themselves as well, you might be asking this yourself, is Power-to-X viable at all? Is it a good way, to use hydrogen and use CO2 for the sustainable future? Is there a business case around this? What Power-to-X actually means, because that seems to be quite ambiguous sometimes as well. So this is what I want to explore today in here. So what it is, right? So Power-to-X, what it is. I've got a very high-level diagram here, so sorry about my graphical skills, but just wanted to represent a very crude way how this works, okay? So if you look at this diagram, we of course have renewable energy, or green energy in principle, whether that's renewable or nuclear or biomass. We have energy that hopefully doesn't contribute towards global warming, or contributes to global warming significantly less than fossil fuels. So that's clean energy. It's being used for production of hydrogen, and the most common way of doing that for now, in the clean way, is via electrolysis. Okay, so we use electrolysis. We use electricity to split water into oxygen and hydrogen, and that hydrogen is considered green if energy is used from renewables. It is pink hydrogen if you use nuclear. Not sure whether there is a specific way to describe biomass hydrogen, but I would say it's a green hydrogen as well. Blue hydrogen if you use fossil fuels with CCS. Not sure exactly that is the best way for hydrogen, but it is a way, so hydrogen CCS would be a way to get us to the sustainable future, so I guess it is a transition technology. Now, once we have that hydrogen, what can we do with it, right? Some people say we can directly burn it, some people say we can convert it into something else. The issue with hydrogen is it's very small molecules, it's very difficult to store, you have to have very high pressures, so 300 bar and higher, 300 or 700 bar and higher, if you want to store it as a liquid. So this is very energy intensive process. So Power-to-X is the alternative. So Power-to-X means you use power to produce X, where X is the chemical that you produce. So in many cases, we use Power-to-X as Power-to-Gas, where gas is synthetic methane. So we do use CO2, which ideally is of bio origin, or biogenic origin, or atmospheric origin. So that means that CO2 that you have is within the closed loop in the carbon cycle. So you use CO2 from the air to grow biomass. That biomass is being combusted for power generation, and then you can use that CO2 for synthesis of chemicals that, when combusted, then release energy, but also go back to the atmosphere, and then you close the cycle. So we have to think about the origin of CO2, because if we do use CO2 from fossil fuels, we just shift the emission point. So using fossil fuel Power-to-X based on the fossil fuel CO2 will not make much sense in terms of the climate support. Okay, so we use that CO2, we combine it or react it with hydrogen to produce X. In this case, gas, synthetic methane. That's what I'm going to talk about in a minute. So Power-to-X means we convert power into the chemical that we can store. Methane, a little bit easier to store than hydrogen. Methanol is a potential technology that might be the future, where you basically convert CO2, hydrogen, into methanol and store it as a liquid. which is a little bit easier atmospheric conditions. The synthesis is a little bit more energy intensive than, or maybe not energy intensive, but capital intensive. So it's all down to the cost at the end of the day, right? So that is something I wanted to show you today as well. So Power2Gas, I've already shared this figure with you the other day or last week in my newsletter, but basically this is the main idea for Power2Gas, where you basically use power from renewables and you synthesize synthetic natural gas. So that you've got this, people say surplus electricity. Well, it's not always the best way to explain surplus electricity, but if we can avoid curtailment of renewables, that's best. That's a great idea actually, because you can use that to produce hydrogen, then you can use that to produce synthetic methane. So we produce hydrogen in electrolysis. We do use hydrogen for methanation, where you use CO2 to produce methane, and that methane can be re-injected to the existing infrastructure, in existing natural gas grids, existing gas boilers, and so on. In this case, what we evaluated was whether we can have a cycling process where you basically use that methane later for oxy-combustion to release that energy, and then you capture the CO2 and you reuse the CO2 as the cycling process. In terms of the overall efficiency of this kind of solution, it is usually about 20 to 35%, the round-trip efficiency from power in renewable source to power output to the grid. So there is quite a lot of energy loss in there, okay? But this might be the way that we can do it in the future if we can find a way to improve the efficiency of hydrogen production and improve the efficiency of power generation, because ultimately it's down to those efficiencies, down to those conversions that reduce the overall conversion of the system. But what is more important, when I was preparing for this live, I thought what would be the most important to demonstrate to you. And I drew from the basic process design principles, because I've been reviewing some of my lecture notes for process design. And the ultimate way to assess how the technology is, how much viable it is to look at the mass balance, energy balance, but also the gross profit, right? So gross marginal profit or gross profit, it refers to the operating cost of the technology based on the reaction rate, based on the reaction equation. So it doesn't account for the capital cost. This means that if your gross marginal profit is positive, then there is a chance that this process will be viable, economically viable. If your gross profit is negative, then there is no point going with that in that direction, because even if you add the capital cost on the top of it, then of course that would not be viable, right? So let me show you what I did. Well, I did show you, and now I will explain that in a minute as well in the WSIM. So I did show you that I started working with the methanation in the WSIM, and I did some simple mass and energy balance over there. So based on that mass and energy balance, I do know that to produce 1 kilogram of methane, I need half kilogram of hydrogen. I need this amount of energy to produce that hydrogen, and I need this amount of CO2 to produce 1 kilogram of methane. It doesn't really mean that that hydrogen goes directly into methane, because the reaction actually is hydrogen plus CO2 gives me methane plus water. So the water part, or water vapor in this case, it takes quite a lot of hydrogen out of the system. So that's additional conversion loss, meaning that we only convert a fraction of hydrogen energy into the methane energy. Okay, hopefully that makes sense. So happy to share some of those mass balance equations and mass balance stuff later on. But what I really wanted to talk about is the viability of that solution. So in terms of the cost, right? Because this is where it gets tricky and interesting for me personally. So if you look at the cost, I assumed that we have average cost of hydrogen of £5 per kilogram. We have the cost of CO2 of 100 pounds per ton of CO2. We have a cost of electricity of 150 pounds per megawatt hour. Quite high numbers in this case, but what I really wanted to show you is how this all depends on the cost and how this influences the gross marginal profit. So if you work out, if you use those costs as the initial ones, if you work this one out, you get that the synthetic natural gas would cost about 2.7 pounds per kilogram, and that doesn't account for capital cost. It's just based on the operating cost. Then the revenue from from the SNG, that's the original SNG, that that you basically say that you already have, right? So that should be the current. So that's the revenue from the SNG is 0.5 point this, right? So this is sorry, I don't see it because of my microphone. So basically, if we consider the current prices in the UK, the current gas price, of course, it might have changed recently, but if you consider 4 pence per kilowatt hour, and we consider average heating value of natural gas of 47 megajoule per kilogram, this is the revenue that you would expect. That this is the minimum cost, the maximum cost that you would expect, right? So this is how much it costs right now. With SNG, it's synthetic natural gas, this is the cost. So you can see it's 5 times higher. So if I quickly switch to my DWSIM, so you would be able to see it now. So you see my DWSIM. Happy to share some of those stuff. And if I go to my calculation block, so you will be able to see my calculations. You can see that at this prices, 150 for electricity, so that's pounds per kilogram, sorry, I have changed that. Hydrogen cost of 5 pounds per kilogram, carbon dioxide cost of 100 pounds per ton. We can work out that the total SNG cost should be, the minimum SNG cost should be 2.7, 2.8 pounds per kilogram of hydrogen, of methane. But the current gas cost is about 0.5, right? So that means we would increase the cost 5 times. Where it gets interesting is if we assume that, you can see that the cost of electricity is not really high, right? Because that cost is only relating to the operation of the methanation unit. The main cost component comes from the hydrogen cost. I didn't consider the hydrogen cost relationship with the electricity cost yet. That's the next step. But if I reduce the cost to 2 pounds per kilogram, still my gross profit margin is negative, which means that technology is not viable. If I reduce that cost to 1, then it's still not viable. You can see I will need to reduce the CO2 cost to 50 or even to 0. If I have free carbon dioxide, if I have hydrogen cost of 1 pound per kilogram, only then the system breaks even with the current gas price. Okay, so that's what I wanted to show you, that going power to gas without any carbon credits, without any subsidies, might not be the most feasible way for storing hydrogen, mostly because you would need to have very low price of hydrogen for that system to break even with the existing gas prices. If you allow for some increase in the gas price, of course, then we would be able to do this. Then we would be able to do this. Okay, so hopefully this gives you more or less an overview of the viability of that technology, and hopefully that's useful. Okay, let me know in the comments whether that's useful. So coming back to my presentation now, I just wanted to briefly summarize that basically PowertoGas will need the support, and the study that we did with my colleagues in Spain actually showed that there is a quite large support needed. So this is in euro per megawatt hour. So you would need quite a lot of governmental support and subsidies to make that viable and kind of comparable to existing fossil fuel based natural gas systems. Of course, as the price of electrolyzers will go down, as the price of hydrogen will go down, then potentially we can talk about this solution as the alternative. But whether that will happen and when that will happen, that still is something that we are working on as an academics, as a consultants as well. Okay, so happy to provide those resources. I will link back to those resources in the comment section later on, so that you can easily achieve those, okay, or get those, right? So how do we get there? The collaboration is key. That's what I always emphasize. That's all what I always say, is that we do have to collaborate to innovate, right? We do have to collaborate to get things done. So how we can collaborate? So there are two ways I usually collaborate with people, and that's both training and research, right? So training, well, I've been asking you stuff recently on LinkedIn. You've probably seen that, where I've been asking you what kind of training you need, what kind of skills you want to develop, where do you want to be in about 6 months or 12 months in terms of training. This is all because I've been thinking about how we can support, how me and my team can support you in terms of getting the awareness up, getting the net zero skills up. So this is an ongoing process. So if you're interested in training, please do reach out to me. I'm happy to explain what we currently do and what we've got planned for the next year. In terms of research consultancy, so research-wise, running a couple of exciting projects that we are looking at hydrogen production, we are looking at carbon capture storage, and how we can make those technologies more efficient and more cost-effective. But I'm also developing a number of research proposals in the space of direct air capture and CO2 utilization, where I'll be looking for collaborators. So if you're interested in working with me, whether you're academic or whether you're from industry, whether you want to work on that subjects, please do get in touch, because I'm always having ideas to explore and there is not enough time to do it, right? So collaboration is key because you can pull more resources together. Consultancy, of course, we do consultancy work and we do support each other via our skills. So that currently running a couple of techno-economic lifecycle assessment consultancy projects that I'll be sharing details about fairly soon on LinkedIn. Of course, subject to client saying that it's fine to share stuff. Okay, so these are two ways I can see for us to work together. These live sessions will happen every 2 weeks, and I'll keep updating you about the progress. So some of them will be focusing on the specific concepts, like today, PowertoGas. Some of them will be focusing on the projects that I'm currently running, or teaching or training projects that I'm currently running. So any questions you've got about this, feel free to ask. Okay, so this is all I've got prepared for the main part. So if you've got any question about PowertoGas, about DWSIM, or about modeling of those technologies, please do leave a comment below. But right now I wanted to talk about some of the questions that you may have had. So I received a couple of questions that were pretty exciting, I think, and some of them actually relate directly to energy storage. Some of them relate to sustainability overall, and I will just read out the question and will just provide my answers. And if you've got any questions in the meantime, please do let me know. I'm checking my LinkedIn live so that I can see whether there are any questions. If not, that's right. I'll be answering questions after this session as well. Okay, I can see some comments over there, which is lovely. Great to see comments. Thank you, everyone. So the questions that I received before the event, let me just quickly go through them. So the first question was, is it possible to directly store energy from wind or renewable energy? In principle, I guess in the form of electrons. So energy storage is always tricky because electricity on its own is a form of energy that cannot be stored, right? It's not easily stored, I would say. So we usually have to convert it in another type of energy or another material. Like with PowertoGas, we convert electricity into gas that contains the chemical energy that can be released later on. So I don't know, well, maybe there is a way, but usually you do have to convert the electricity from renewables into something else that can store that energy. Okay, so this is the main difficulty about energy storage, and in many cases, the most say a common way of storing energy right now is pumped hydro, right? So pump hydro energy storage, where you basically use electricity to pump water up the hill, and then when you want electricity, you want to take electricity out of that system, you basically let the water go down the hill, and drive the turbines to produce electricity. So that's the most common. 95% of the total energy storage capacity globally is pumped hydro. I can see an increase in battery energy storage, so that's quite significant increase over the next years expected. Battery energy storage, but also compressed air, liquid air energy storage is kind of promising. And actually, some of our projects hopefully will be looking at the energy storage, how we can improve that, what are the new ways of energy storage at large scale. Okay, we'll be updating you on that as we go along. Another question is driving electric vehicle sustainable, or does it depend on where the feed electricity comes from? So this is a very good question, I would say, because we've all been told, or we kind of see the switch towards hydrogen vehicles or electric vehicles. So in terms of electric vehicles, I would assume that it is more sustainable in terms of the greenhouse gas emissions, but that depends on where your electricity is coming from, of course. If your electricity is renewable, then, well, you've got that benefit that your energy source is clean, okay? But then you've got an issue with the battery manufacturing. Where is that battery being produced? How is lithium being extracted? How is it being processed? What's the life cycle emissions associated with that lithium battery? So this is something that we are not looking at. This is something that needs to be evaluated. But in principle, I would expect that EVs will be more sustainable than fossil fuel cars right now. And of course, it depends on where you take your electricity from. In terms of the cost, of course, the EV version of vehicles are more expensive, mostly because of the battery cost, I believe. But from what I can see and what I can read, that the operating cost, so your fuel cost, will be significantly cheaper. So there is a balance in it, okay? Another question is, and I basically touched on this earlier today, is producing hydrogen from green sources economically viable? And what is the business case behind that? What's the decisive step for the business case? So from what I know, currently the green hydrogen usually varies between 3, 4, up to 6, 7 pounds, dollars per kilogram, depending on the source. So it's still significantly more expensive than that associated with that produced from fossil fuels. So that main issue here is variability of the supply. Because of the load factors, you get quite high price of hydrogen. And in terms of the technology capital cost, you can drive the cost down, and I expect the cost will go down. But then that load factors will always affect how often you can, how stable your production of hydrogen is, and as a result, you might not have a continuous production of hydrogen. You might need to link that with another way of energy storage, right? So I guess business case would be if we can get the cost down for capital cost, if we can make sure that we have high load factors, then there definitely might be a business case for green hydrogen. Of course, there are claims that green hydrogen can go to 1 or 2 pounds or dollars per kilogram of hydrogen. I believe this is viable, but again, not sure how fast we can get there. And another question was, what does P2X mean? I've already explained that in the presentation. So P stands for power, which is the electricity source from renewables, ideally. 2 means the conversion, right? So you convert power to X. X is the chemical that you convert that power into. So that's the brief explanation of the acronym P2X. We usually use P2G as a PowertoGas. We can use P2L as a power to liquid, where you produce methanol from power, for example, using the methanation process. Okay, so that's all the questions I had before the session. Let me quickly have a look at the chat so that I can see whether there are any questions in the chat right now. And if not, I'll be quickly wrapping it up. Okay, it is right. So very good question. There is Good question about syllabus, which should be taught to chemical engineers to get good hold in energy transition. So chemical engineering, it's one of the major study area that our work focuses on, and we've got very good courses on that subject actually. So if you really want to go into energy transition, say you've originally started with oil and gas and you want to transition to green energy, for example, you basically have the skill set, right? So this chemical engineering skill set is more or less the same, right? You've got process design, control, measurements, you've got process control, process measurements, you've got techno-economics as well, so economic analysis. But the thing that is currently missing in many cases is lifecycle assessment, sustainability analysis, entrepreneurship. So this is something that I would assume would be important for future chemical engineers, mostly because, as we can see, there's lots of startups coming up in the area of carbon capture, direct air capture, hydrogen, and that startups will need entrepreneurial chemical engineers. So if you can develop those skills, that would be very important. But also on the technical side, I believe AI, machine learning, programming will be increasingly important, because you would see an expansion in use of AI in chemical engineering over the next couple of years. Happy to elaborate on this further, happy to provide some additional information on this. Very good question. Thank you very much. Let me quickly go through a couple of new questions. Syllabus. Yeah. Thank you, Nasser. I guess you produce 100 megawatts from solar energy. That's quite a large project. Would be keen on learning more about this. Right. We don't have any more questions live. If you have any questions after this stream finishes, feel free to leave them in the comments. I will also upload this video to YouTube. I'll upload that into my LinkedIn account as well, so that you can get access to this. And just remember, this episode, this Net Zero academic live sessions are aiming to discuss the topics on the green energy transition. So I'll be talking about all sorts of technologies, and hoping that you engage in the discussion. So if you've got any questions you want me to answer in the next session, which will be in about 2 weeks' time, if you've got any topic that you want me to talk about, please do let me know. So to summarize, today I've showed you that PowertoGas, it could be a viable option. It's not entirely crazy, but let's see how the future will pan out. More research is done, it's being carried out right now, more research is required, and I'm eager to collaborate with you to make this technology happen in the nearest future. Thank you for your time, and it was wonderful to share those insights with you. Have a great time. Thanks.